Bismillahirrahmanirrahim. Okay, let's continue with the slide chapter B. Synchronous generator, basic parameter which operate in a standalone mode. Okay, for this chapter B, we shall discuss on the next example of example 2 here. But meanwhile, before we start this discussion, let's recap on the topic of trigonometry and trigonometry. Okay, as we can see, if we have a square wave, triangle, which is the angle of theta here. So this is our 90-degree angle. So this is our hypotenuse from this point. This is our hypotenuse of the theta. So this is our adjacent, this is our opposite side of the theta. Okay, we have learned from my previous method, we have simplified this kind of trigonometry equation into so, cha, and toa. So means what? Sine theta is equal to opposite over hypotenuse. Meanwhile, our cos theta here is adjacent over hypotenuse. If toa here means that our tangent theta is equal to opposite over adjacent. Okay, so you should remember this, and you should remember this basic trigonometry such that it can be applied when we want to calculate the vector of our voltage, current, and whatsoever in our calculation to come. Okay, so sine is equal to opposite divided by hypotenuse. Cos adjacent divided by hypotenuse. Tan is opposite divided by adjacent. So So remember this. So let's say we have here our which is equal to IAXS. We have learned that when we have a by the way, means that our opposite here, if you want to find the opposite value, so opposite is equal to hypotenuse times sine theta. If we're looking for our adjacent, so adjacent is equal to hypotenuse times cos theta. And opposite also, if we have a formula of tangent, is equal to adjacent tangent theta. So this is going to be applied in our calculation of our vector that we shall learn in the coming time. So if we remember or recap again the equation for synchronous generator, so E is equal to IA times RA plus IA times XS plus the V phase that produced at the load terminal. So if we draw again in terms of phase diagram, so if we use V phase as our reference, so V phase at 0 degree, V phase at 0 degree. So the following current, let's say it follows by certain degrees of lagging power factor. So here are the theta. Then our next value of IAXS here will be 90 degree of the value here, and 90 degree of the value of the current. So the current at the certain power factor. Meanwhile, this IAXS is at 90 degree of the current. So if we shift all together to this side, we shall have this is our IA XS. So we shall have a IA XS here instead of place here. So we shift to the N side. So it means that we have voltage plus IA XS here. Then at certain area, this IARA is neglected, so it becomes 0. So by right, we have another lines here for IARA, but since that we assume RA is equal to 0, so this is a simplified version of our diagram will become only V phase here and IAXS over there. Then this is the sum of our EA. So EA will be only the sum of IAXS plus V phase, because this amount is now 0. Okay, then how to calculate this magnitude? How you want to get this magnitude? So we have magnitude of V phase, we have magnitude of our IAXS here. So this is obtained by the trigonometry concept. So it means that if we have our theta here, so when we shift to this side, so with the angle of 90 degrees, if we prolong the line, so here will be 90 degree of IAXS here compared to our current. Then if we make another line of 90 degrees line here, so here will be our 90 degree, and this angle will be the same theta angle of this one. So now we have a trigonometry angle over here. So if we shift to the bigger scale, so if this is our theta, so this is our JXSIA. So here will be your adjacent opposite. So you use this formula, opposite and adjacent here. So it means that we have A is equal to H, which is IAXS sine theta. Meanwhile, we have O of IAXS, sorry, A is cos theta. A is cos theta. Meanwhile, your opposite is sine theta. Okay. A is cos, opposite is sine theta. So you insert here. So we have A, we have a O here. So later, when we want to calculate for the amount of EA, just now, so EA is the amount of V phase here plus the values of O here. We calculate this now. V phase plus opposite here, which is IA XS sine theta. Over here is our IA XS cos theta. So EA squared, trigonometry for this this triangle is equal to V phase magnitude plus IAXS sine theta squared plus IAXS cos theta squared. So you shift to this side, so EA will become third of all of this. So this is the amount of EA magnitude. Calculate from this concept of trigonometry. Okay, that's a revision for trigonometry. So let's proceed back with our example 4.2 here. So what is the speed of the rotation of this generator? Okay, if you calculate the speed, it's right here, electrical speed, so it's equal to 120 F divided by the number of poles. So we have here 4 pole, frequency of, how much is the frequency? So wait, it is 60 Hz, so 120 times 60 divided by number of pole, which is 4. So we shall get a value of 1800 RPM. 1800 RPM. This is the electrical speed of this machine, or synchronous speed of this machine. How much the field current must be supplied to the generator to make the terminal voltage 480 volt at no load? So 480 volt at no load. So actually you can use directly refer to this graph, but we have to because it depends on connection of this motor. Is it connected in Y or is it connected in delta? So by that we have to write the diagram, sketch the diagram and calculate from that. But seems like when we have a delta connection here, so it means we have a delta connection. If we connect to the load, so V phase will be the same as V terminal, and V phase is the same as V terminal. So we have here 480 volt terminal voltage, so 400, 450, 480 is around here. So when we make a projection line, so we'll go down to almost 4.5 or 4.6 ampere. Okay, 4.6 ampere of field current to produce a 480 volt of open circuit terminal voltage. So means that how much the field current must be supplied to the generator? It's around 4.6 ampere. So you use a ruler and to probe or project on the expected current. Okay, if the generator now connected to the load and the load draws 1200 ampere at 0.8 power factor lagging, how much the field current you will require to keep the terminal voltage equal to 480 volt. So we put for 4.6, we have 48 at open circuit. But when we put a load, how to maintain this 480 volt? Like what we can see when we have a V out here, we put in more load, so the voltage for sure will drop. Is it? So how much the drop? And how much we have to increase in terms of our field current, such that the drop at this point we maintain at 480 volt instead of this drop. Okay.